the next talk will focus specifically on lutetium hafnium, mostly. As I've showed, the partitioning of lutetium hafnium and samarium is essentially identical. There's a bit of a difference in magnitude. So everything that I talk about for lutetium hafnium, we can apply to samarium neodymium. The numbers will be different, the magnitudes of the variation will be slightly different, but they're essentially the same. And what this system is most useful for is looking at the evolution of the continental crust, particularly through minerals like zircon. So, whereas I showed previously that the oceanic crust is sort of, very young, it's quite an ephemeral visitor to Earth's surface. The continental crust lasts a lot longer. There's much more age heterogeneity. You can see this map here shows different geological provinces that sort of range in age from the Archean all the way through to the present day. And when you compile databases of things like the age of zircons formed in granites and origins, you see that there's a huge amount of heterogeneity. So there's not a lot of material preserved from the Archean, but there's periods in Earth history where there's much more material preserved. And people have speculated about what exactly that means, right? Whether that means that are there periods in Earth history where you're forming more crust and you're taking more crust out of the mantle, or is there some kind of preservation bias that's superimposed on that? Because we know from most continental crust today is produced in subduction zones, and subduction zone volcanism is kind of a continuous process, so it's hard to imagine how you might get this kind of episodicity imprinted onto the geological record if most continental crust is formed in that way. So what we want is essentially some kind of chemical discriminator that can tell us whether a piece of crust came out of the mantle or came by remelting old crust that and form magmas and constant crust in subduction environments, but you can also form them in intracontinental environments where you don't have any material coming up from the mantle. You're just reworking old crust like sediments. Pete showed a nice image of a S-type granite that had lots of inherited zircons, right? And that granite clearly formed by remelting all the sediments that were there in order to get all the zircons in it. So what we would like to do is come up with a curve like this that describes when continental crust was added, or how it accumulated over time. And people have been thinking about this problem for a long time. So Burley and Rand initially tackled it in 1969, and over time others have tried to improve on that. And you see that there's some of the earlier models have very, very little crust forming early on in Earth history, and most of it coming in sort of after 2 to 1 billion years ago. But over time, that sort of has been pushed back the other way, and now some of the younger models, or the more recent ones, show that most crust probably formed 4 billion years ago, between 4 and 3 billion years ago it formed, and that the rate of continental growth has decreased since then. So what we're going to show with the hafnium isotopes is how we can sort of get a handle on this problem and try to come up with some of these curves. So I've shown this kind of thing already. Take out the K scheme, we can generate an age equation from that, which then essentially tells us how we can relate isotope ratios that we measure to, see there's a mistake there, that should be lutetium. Again, just a summary of how these systems work. Essentially, they're all incompatible elements, but the parents are less incompatible daughters. So you end up with, the liquid or crust that you extract out of the mantle can be depleted in samarium and neodymium relative to lutetium and hafnium. And you can see that their partitioning behavior is basically identical. So in theory, they should behave identically. When you plot up isotope ratios of hafnium versus neodymium, you can see that's the case, right? For most terrestrial crustal mantle rocks, they lie along this very nice linear relationship. It's not exactly one because the lutetium and samarium are retained in the mantle sort of slightly differently, but generally they give us very consistent results. So again, you can kind of think of them as telling you the same thing. So in order to try figure out when crust was extracted out of the mantle, we need some kind of model of how the mantle has evolved over time. What we can do is we can measure the present day composition of primitive meteorites or chondrites as our sort of representative sample of what the bulk silicate Earth might look like. And we measure its hafnium isotope composition and its lutetium hafnium ratio, and you can project that back through time to 4.5 billion years ago when the Earth formed, and that gives you that green curve there. You can do a similar thing for the depleted mantle. So its present day composition is somewhere up there. It's slightly more than the bulk silicate Earth because it's been depleted in hafnium or enriched in lutetium, you can think of it that way. And project that back as well. And it also, that's this dashed line here. Goes pretty much back to the BSE at the initial. You get close to what your BSE composition is at the age of the Earth. And fine detail is not exactly there. Whether that's a realistic model is up for debate. So there's a lot of people have measured the isotope compositions of old rocks and minerals now and shown that they're very similar to your chondritic values, which implies you didn't have a depleted reservoir back then. Yeah, it's a model. It's the best we've got. We have to hang our hat somewhere. But yeah, so some other models essentially have crust formation and depleted mantle formation, mostly happening at 3.8 GA, and then essentially what you need is a higher lutetium hafnium ratio in order to get to the present day depleted mantle composition. You can also then draw curves that describe how crust would have evolved. You started off with the bulk silicate Earth, took some crust out, formed a depleted mantle. That crust would have evolved along some trajectory that would go to less radiogenic initial hafnium compositions than our bulk silicate Earth. The slope of these lines is defined by the lutetium hafnium ratio in the crust, which for felsic rocks is about 0.015. For maker crust, it might be slightly different and it would evolve along a steeper trajectory. And then you can imagine if you form crust at different times. So presumably if you formed the depleted mantle at 4.5 GA, you would have formed some complementary crust that would evolve like that. And if you formed at 3.8, you'd form some complementary crust, and then you can imagine subsequent crust coming out of the depleted mantle would form along essentially parallel curves. And it works exactly the same way in epsilon hafnium space. So all we're doing with epsilon hafnium is we're normalizing to the BSE value. So we're flattening that BSE line and then looking at the deviation from that. And it's just a way of recasting our system into units that are easier to think about. So you're not looking at numbers that are, at the third and fourth, fifth decimal place. You can think of it in whole numbers. So how do we measure them? Well, Zircon is our friend again. It's, as Pete mentioned, very abundant in felsic igneous rocks, physically, chemically inert. Got some crystals here that preserve multiple growth zones. So you've got these nice oscillatory zone rooms and cores. And because it's very inert, you can preserve, the initial and primary chemical signatures of those rooms and core domains, which can tell you about the environment they grew in at multiple periods in time, potentially. But importantly, it's probably the, zircon and hafnium sit right beneath one another on the periodic table. So zircon is the major repository for hafnium in the continental crust. So it allows us to get quite precise hafnium isotope compositions of the magmas from which that zircon grew, which we can then plot on diagrams that we saw previously. So what we do is, I'm going to talk more about the systematics. I'm not going to go into the measurement really. There's issues with the measuring hafnium isotopes. I'll just want to say that there's interferences on the 176. So there's 176 lutetium, which is the parent, obviously. And there is 176 ytterbium, which we also have to cancel out. There's some good papers by Chris Spencer and Chris that sort of outline all that information. More just how the systematics work. What we do is we measure the zircon today in the lab. We measure its initial hafnium isotope ratio, corrected for interferences, and we can, or not the initial, we measure a hafnium isotope ratio. We measure the lutetium hafnium ratio, and then what we do is we have to correct that back to the age of the crystal, right, to get what that hafnium isotope ratio was at the time the crystal grew. The zircon, that lutetium hafnium ratio is very, very small, so the initial corrections, you can imagine this line is essentially being horizontal. So it's not a huge issue really, but for other, if you wanted to try this in other minerals, that might not be the case. So once we've got the initial ratio at the time of crystallization, we can see, does it plot, below the BSE curve, or does it plot above the BSE curve? Right? If it plots below the BSE curve, that's telling us that it's probably that rock we're looking at was derived from older crustal material that might have fractionated out of the mantle or BSE at some time previously. We can project, if we assume we know what that crustal source lutetium hafnium ratio was, so if it was 0.015, we can project a line back to our depleted mantle curves and extract some time from that, which would be essentially the time that crust fractionated out of the mantle. If you can imagine if the zircon plotted higher up here, the age of crystallization would become much closer to the time of the source component, right, the source of that crust. And in the case where you're looking at a zircon that's derived directly from the mantle, the age of crystallization or the rock will plot exactly on that blue line, and the age of crystallization essentially represents the crust formation age. Again, there's some sort of uncertainty around how you do this, right? There's an assumption you have to make about what the composition of that crust was. So for most granites, high potassium granites derived from old continental crust, the assumption for lutetium hafnium ratio of 0.015 is probably fine. But if you're looking at TTGs, right, that we know are probably derived from melting mafic material, you might want to use a different lutetium hafnium ratio. And the effect of that is, if you assume the source evolved along a steeper curve, it means that it has to have come from an older source material. And then there's obviously the uncertainty about which model you use, but that's, you kind of just have to pick one reference frame and go for it. Another point to make is there's also uncertainty in the age of the sample, right? And that uncertainty in sample age can have an influence on the uncertainty in your hafnium or your initial hafnium isotope measurement, right? Because of this age correction that's involved. In reality, the age correction doesn't impart a huge amount of uncertainty, right? But because we're also normalizing to Epsilon hafnium and BSE, and it essentially means we are normalizing to a BSE value, depending on what age you use, might change the BSE value you use, and that can change the Epsilon hafnium value you get. Just something to consider when you're doing this kind of work, right? Obviously, if you have a very, very precise age, less than 10 million years, it's going to be negligible difference, right? But if you're looking at sort of individual crystals and you don't have very precise ages, if you're looking at uncertainties up north of maybe 50 to sometimes even 100 million years, you're going to get quite a lot of uncertainty in your Epsilon hafnium value that's just a result of that uncertainty in your age, right? Because you can see as you increase DT, essentially, the way the geometry works is that you increase DHF. And, for, I think, you can imagine that being about 50 to 100 million years, you can almost double your uncertainty just from that. There's a really good paper by Ryan Eckert where it goes through all the maths, derives the equations. So if you're interested in this, you can go look that up and see how you can factor that into your calculations. Time. So, what I wanted to mention there. Oh, yeah. There's issues with mixing, obviously, now, right? We can measure a rock and see that it plots here, but we don't know exactly whether that crust formation age is real, right? You can imagine that, and what you see in reality is that when you plot many rocks of a given age, that you'll find these vertical arrays and have hafnium isotope space. And what that implies is that you're mixing sort of, a given analysis could be a mixture of something that's more depleted with something that's more enriched, or some older crust that's mixed with mantle-derived magnets, right? And what we need to do is to determine whether the model ages we get, right, or these crust formation ages are real or not, is to say whether that analysis we're looking at is a mixture or a real crust formation age. And we can't do that with hafnium isotopes alone, unfortunately. We have to incorporate some other information. So what people have done is looked at oxygen isotopes, and I think Chris or Jana might talk about this later on. Pete briefly touched on it. Essentially with oxygen isotopes, what you can, we know what the oxygen isotope composition of the mantle is. It's less than 6.5 per mole. So we can measure the oxygen isotope composition of our zircon. We can measure its hafnium isotope composition. And we can say, okay, well, we know that if the oxygen isotope composition is greater than 6.5, that zircon probably grew from a melt that was derived from pre-existing crust and doesn't represent a new mantle addition, right? But if the zircon has a oxygen isotope composition that's less than 6.5 or within the mantle range, then we can infer that that zircon grew from a melt that was derived from the mantle and does represent a new addition to the continental crust. And that's what Tony Kemp and others, I think Pete, you were on this paper as well, I believe, showed in this diagram that you have, a bunch of different zircons that fall on different arrays, and there's some mixing between the two, right? And that most of the zircons that show mantle-like oxygen isotope compositions fall on two distinct arrays, which you can infer represent two distinct additions of material into the continental crust. And that all these zircons that lie in between represent mixtures of those two components. We see similar things here in the Albany Fraser origin in Western Australia. So had a lot of zircon hafnium isotope data from that region. And what you see is all the data form these huge vertical arrays that lie, if you projected them back to the depleted mantle curve, would fall between 2.2 and 2.6. And we know from just dating the rocks that there's no magnetism happening at that time. So clearly, these arrays that we see are mixtures between some older Archean components and the younger Proterozoic component. We superimpose the oxygen isotope data onto those analyses. You see that initially the model age distribution is this kind of normal distribution that's centered around 2.4, right? Which is where we know there's nothing happening. But when you filter it according to the oxygen isotope composition, that normal distribution gets split into a sort of bimodal distribution with some peak at 2.7, which reflects mafic magnetism in the eastern goldfields, and another peak at around 2 GA to 1.9, which we know is roughly the source for much of the material we find in the nuclear basement. So that is essentially then how we build up these curves, right? And that's what Dweem et al. Did in their paper. They took hafnium isotope data from a global database, applied oxygen isotope data to it, and then counted the cumulative sort of frequency histogram of those oxygen isotope filtered model ages. And they showed that most of the continental crust, or at least 75% of it, probably formed before 3 billion years ago. And then at 3GA, there was some kind of change in the rate of continental crustal growth, decrease. And they infer that, that rate of change of continental crustal growth might reflect the start of plate tectonics because it happens at a time, and we see a number of other changes in the geological record. A little bit of time left. So another application we can use with this, because essentially what we have is a fingerprint that tells us, did this rock we're looking at come from the mantle, or did it come from the crust? We can apply that to mineral systems, because we know the mantle is much more enriched in metals than the crust is. So where you have places in space where there's been more mantle input into the crust, you tend to find more metals. And this kind of application has been used in the Yilgarn craton. So I think Steve Wash, is it? Yeah, and Dave Moll and others have collected lots of neodymium isotope beta and hafnium isotope beta and plotted these maps, which essentially show the spatial variation in neodymium and hafnium isotope composition. What you see is that in the eastern goldfields, you've got much more juvenile, so more depleted isotope compositions, and the depleted zones tend to be where the bigger gold deposits are as well. So in the eastern goldfields over here, and then you have some Murchison, the Cathara greenstone belt up there, as well as I think that's the Boddington gold mine down there. They all lie in these zones of high depleted crust. But we can also use it to say something about tectonic processes, right? So based on the geology and sort of geochronology, Bill Collins proposed this idea of what do you call it, tectonic switching, right? Whereas, at a given subduction margin, we might get periods of extension and compression at different periods in time, depending on the dynamics of the buoyancy of the subducting slab, right? So in some periods of time, the slab's going to be quite dense and it's going to be rolling back. And what's going to happen then is you're going to extend the crust in the back arc. And when you extend the crust, you'll get more sort of juvenile magmas coming into that back arc area. Whereas, if the slab is more buoyant, it's going to push forward, and that's going to push the back arc into compression, and you're going to get more crustal reworking and less mantle additions during the compressional periods. And we can see that kind of process in isotopes as well, right? So if we plot, again, the isotope composition versus time, you can see that in the Lachlan Fold Belt in Western Australia, where these ideas were kind of first developed, see they initially start quite low, implying that you're reworking old crust. And there's a period where they go to sort of positive epsilon, neodymium, and hafnium values. So implying there's juvenile addition at that time. And then they go low again, and then they go up again. So it shows that this, the Lachlan Fold Belt, like Paul suggested, formed through this kind of dynamic process where you have periods of compression, periods of extension, and periods of compression again. And it's useful to see that we can pick out those kind of dynamics just using the sort of time resolved isotopic signals. Paul then went on to apply this to a much grander scale. So they had a paper in Nature Geoscience where they suggested that you can distinguish different type of ocean basins essentially using these time resolved hafnium isotope signals. So external ocean basins like the Pacific, where you've got sort of subduction girdle going on the whole oceanic basin that's contracting and slab rollback over time, should over long periods of time show these secular shifts to very juvenile isotope compositions, and that essentially reflects that as you close that basin up, you're extending the crust sort of almost all the way around it, and then the hafnium isotope composition is going to go more juvenile. In other ocean basins, like in this case the Tethys, or something that might eventually the Atlantic Ocean might turn into one day, you're closing them from both sides, so you're reworking crust on both margins, and you're going to get these divergent hafnium isotope arrays. So instead of everything going towards juvenile values, you're going to get reworking to old crust and juvenile addition at that time. I think people have tried to apply this back to older ocean basins. I'm not sure how well it works, but yeah, it's something you can potentially do as well. And I think that's it. So yeah, thank you very much.